In this module, we will use principles of chemical kinetics to help us in predicting shelf life of foods. As we have seen in other tutorials, that quality of food undergoes a change during storage and distribution. Changes in a specific quality attribute, let's say A, with the time t, can be mathematically shown using chemical kinetics as follows. dA over dt, and we will use the sign plus minus, is proportional to the concentration of A raised to power n. We will call it equation 1. The left-hand side of equation 1 states that the rate of change of A with time is expressed as dA over dt, which may increase or decrease. The reason why we use the plus minus sign, depending on whether the concentration of the quality attribute is becoming larger or smaller during storage. The rate of change is proportional to the concentration of the attribute A raised to power n, where n is the reaction order. Equation 1 is a general rate equation. In equation 1, we remove the proportionality and introduce a constant k, where k is the reaction rate constant, and that gives us the following equation: plus minus dA over dt equals k times the concentration of A raised to power n. So this is our equation 2. Now let's look at those reactions that follow a zero-order kinetics. So we have our general rate equation that we earlier obtained as equation 2, that is plus minus dA over dt equals k times the concentration of A raised to power n. Then for zero-order reaction, when the concentration of A is decreasing, then we can write minus dA over dt equals k. Since n will be 0 in equation 2 and A raised to power 0 will be 1. So k times 1 will be k. So on the right hand side we have only the rate constant k. So and that is our equation 3. So next we will convert this differential equation 3 into a more useful form by integrating it. Now you will recall the way to integrate a differential equation is to first separate the variables. And the variables here are the concentration and time, since both of them are changing, and k of course is a constant. So we write minus dA on left hand side equals k times dt on the right hand side. So we have separated the variables in equation 3 to obtain equation 4. Next we can integrate the left hand side from some initial concentration A0 to a final concentration A, which will be from some initial time 0 to final time t, respectively. So we can write minus, and we use the integral sign from A0 to A for dA, equals k and an integral sign from 0 to t for dt. And that's our equation 5. Now we can evaluate the integrals. So we have minus, and the integral of dA will be A. So we have A evaluated at A0 and A equals, again on right hand side, k is a constant, so it is outside the integral, and the integral of dt is t, and the t, which is the time, is evaluated from 0 to t. That gives us equation 6. Now we can go ahead and substitute the values for the limits. So we have minus, and in parentheses we will have a minus a0 equals k, and again in parentheses we will have t minus 0, giving us equation 7. And this gives us our final equation, a0 minus a equals k times t, our equation 8. Note that the left-hand side in equation 8 is the extent of reaction. In other words, how much of the reaction has taken place in that time period. From shelf life standpoint, a0 minus a is an indication of how much of the concentration of quality attribute has changed during that time. This information will be useful to us in calculating shelf life. In the above equation, we can replace A with concentration of A at the end of the shelf life, and we will call it AE. Remember, A0 was the initial concentration of that quality attribute. And also, on the right-hand side, we will replace T with TS, that will be the shelf life. In other words, starting with some initial concentration A0, going to a final concentration AE during the total time TS for the shelf life. By substitution, we get A0 minus AE equals K times TS. Now, we can take TS on the right-hand side and move all the other quantities on the right-hand side, and we get A0 minus AE divided by K. Note that K is the zero-order rate constant. Also, we observe that equation 8 on the top is an equation of a straight line. Note that straight line equation is often expressed as y equals mx plus c, where m is the slope of the straight line and c is the intercept. So we can express equation 8 in a graphical manner by drawing the ordinate as a and x-axis as t. Then the slope of the straight line that we will obtain will give us minus k, the zero-order rate constant. So this is how we will obtain the zero-order rate constant when the concentration is decreasing with time during the shelf life of a given product. And we will see this with an example in a different tutorial.